First speaker is Professor Mathieu Bauchy from University of California, Los Angeles. His talk's title is From Lab to Field Using AI to Decarbonize Concrete at Scale. He's an associate professor in the Civil Environmental Engineering Department at UCLA. His research focuses on decoding the physics governing the behavior of construction materials by means of simulations and artificial intelligence. He's also a co-founder of the clean tech startup Concrete AI, which uses generative AI to prescribe new concrete formulations that are both less carbon intensive and more economical. With that, Professor Bauchy, the floor is yours.
Yes, so I'd like to tell you a little bit about the effort that we have been doing to decarbonize concrete, but specifically how do we go from what we can do in the lab to really upscaling the results to larger scale and really impacting the field. Okay, perfect. Yeah, so like that's really what we're trying. That's the big problem that we are trying to solve is like, as you know, concrete has a big carbon footprint. I think the scale of it is one thing, but the biggest problem that I see is that all the other industries are really doing some big efforts to decarbonize. And when it comes to concrete, we really are dealing with, to some extent, thermodynamics, and we're already close to maximum thermodynamical efficiency when it comes to clinkering and things like that. So, like this number is going to increase if we don't do more efforts to decarbonizing concrete. And so there are many ways to decarbonize concrete, new materials, new types of cement, and that's all great, but if we have to wait 10 or 20 years before we can start decreasing the carbon footprint of concrete, then it's a lost opportunity. Because every ton of CO2 that we release now is like a depth that accumulates over time. So whatever we can do right now, that's really what I want to focus on. And so we've done quite a little bit of work in my lab in using machine learning. The idea is that we already know how to address the inefficiencies of concrete. Like we need to optimize mixed formulation. We need to reduce over design. We need to make sure we come up with the most efficient recipe. And we already know how to do that. We need to do some trial batch. And the problem is that it's just slow, it's laborious. There is typically producers have hundreds, if not thousands of mixed designs, so they can't go through this exercise one by one. And that's where really machine learning can help really accelerate these types of optimization and make it faster so that machine learning can directly tell you what's the optimal mixed design so that you don't have to go through many iterations of trial and error until you converge to the right recipe that will meet all the targets performance-wise and will have the lowest embodied CO2. And so for this, you need some accurate models. But you need models that can predict every property that can be included in specification. So this is an example here of showing the typical accuracy that we can get. On this plot, you have the predicted property, in this case, the strength on the y-axis, and the true measured strength on the x-axis. So ideally, you want this to be as close as possible to y equal x. And so in this case, typically we can predict strength development with an accuracy of about 500 to 600 psi. But again, we need to be able to do that also for shrinkage, also for slump and setting time, any kind of property that needs to be included in certification documents, then we need to be able to predict that so that whenever we recommend a concrete formulation using machine learning, we can make sure that it's going to perform according to the targets that each mix design needs to satisfy. So what I would like to show you here is one of the first results we ever got by doing what we call a human versus AI competition. So the idea here is that we really wanted to see what's the best that a human can do in optimizing concrete versus what's the best that an artificial intelligence can do. And so the rule of the game here was pretty simple. It's can you come up with a mixed design that's going to have a strength, a 28-day compressive strength of 5,000 psi, and using only materials available at a given plant, right? The idea is not to bring new materials, new low-carbon materials or things like that, and to see what's the best that you can do as a human versus what's the best that machine learning can do. And so here what I'm showing you on those plots is in blue, that's the result that was generated by the quality control person, so that's the human. And in green, that's the mix that was suggested by the AI. And I'm comparing here with one of the reference in our MCA mix. So the first thing that you see here is that the human got too greedy, really tried to optimize too much, and eventually the mix did not meet the target strength. So that's one first thing. Second thing, there was all kind of requirements. It was not just strength for this mix design. It needed to have a target slump. Shrinkage needed to be below a certain level. So like in this case, both of the mix were able to meet those targets. But the big thing is this. So in this case, the target was to minimize material cost. Unfortunately, that's really what producers care much more than minimizing CO2. But the good news is that those two usually go hand in hand. If you can reduce cement, you will reduce cost and you will reduce CO2 as well. And so here, this is really the big thing. It's like here, despite the fact that the mix generated by AI had a higher strength than the mix generated by the human, the cost was much lower. And it's significant, right? It's $7 per cubic yard. So it's probably like 2 times the margin of the producer on this mix. So it's like, there is some significant savings, both in terms of cost and CO2 that can be achieved right now without any new materials. But there are also some challenges, like this was a lab trial. So it's one thing to do it in the lab, but really to scale it is a big challenge. So there is various challenges here that I want to talk about, and then we can discuss it more in the panel. But the first thing is materials. Like different regions have very different materials, and even at the scale of one producer, like each of the plants will have different aggregates, different types of cement, different types of fly ash, things like that. So it's not because you come up with an optimal recipe at one plant that it's going to work at the other plants. So we can't just have a golden bullet that's going to work for every single location. And then there is also variability over time. Like we need to be able to account for the fact that the gradation of the aggregates can change over time. Maybe supplementary cementitious material, fly ash, the chemistry can change over time. So we need to be able to have something that can learn over time, not just a one-time optimization. There is a challenge just due to the number, like, again, various producers, they can have like thousands of mix design in their catalog. So if it takes you like several months to optimize one mix, that's not going to scale, right? So we need some kind of high throughput approach. Then there is everything that is not related to materials only, but like the manufacturing itself. Like what's the role of the plant? What's the role of temperature, the transport time between the plant and the time that the concrete was tested? So there's many things besides just the materials. And again, those things we need to take them into account. Then there are properties for which it's very hard to get data because it's very hard to measure them, or there is no good way to really put a number. But they are still important for producers, like probability, finishability, all those things. If we're going to recommend new mixes by AI, we need to make sure that they are going to feel good in the same way that present mix are feeling good. So it's also a challenge. And then there is data. Of course, machine learning relies on data. So sometimes the data can be hidden in some kind of Excel sheet, can be not organized, or maybe some data is missing. Sometimes, for example, typically the main issue is water, like tracking water in each truck to make sure we can account for the role of water on strength, slump. That's a challenge. Like this data is not always available. So one of the effort that we were trying to do to address those challenges, this is very hard to do in the lab. Like it needs to leave the scope of academia, so that's why we founded this Concrete AI startup to really try to increase the scale that we can tackle. And the idea of this, it's a pure software to recommend how to reformulate existing mix design to reduce their cost and reduce their embodied carbon CO2. So, like the main motivation here, like this slide is echoing the previous challenge one. Here, I like to show you like how we addressed those challenges. So 4 main big things. So first, data. We need as much data as possible. So we have, most of our effort was to collect data. And at this point, we have about 1 million data points. When I say data points, that's what you would see on the ticket, like the exact formulation of the recipe of the concrete, and its strength, its slump, shrinkage, setting time, etc. We need to, we can't stick to one single region. Like we need to have partners across America, because that different regions have very different SEM availability. Like in some region, like in California, sometimes fly ash is more expensive than cement. In some region, you just have no fly ash. Sometimes you have no slag. So you need to work with different people who have different types of materials to have as much variety as possible in the data that you have. The next thing is really high throughput. How can we do this optimization fast? And so for this, we developed an optimization algorithm that can really optimize within seconds, take a given mix design and optimize it within seconds. The idea is that that way, overnight, you can optimize like thousands of mix design. And then the next thing is about data. Like usually, concrete producers are using some quality control or some batch panel software. So if you want to access this data, you need to natively access this. That's really the only way to access data at scale. You need to directly tap into the source of those data. So a couple of achievements so far, like we have optimized over 2 million cubic yards of concrete that went through this exercise of reducing cost or reducing CO2. Average savings, typically, we save both on the cost and the global warming potential. With typical savings is 5% on the cost and 30% on the global warming potential. Again, those are savings that are really achievable right now. Like we don't have to wait 10 years. Of course, in 10 years, we'll have new materials, new types of cement that will allow us to go beyond that. But like those savings are more like, what can we do now? And so we did some kind of calculation to see like, okay, if we were able to use this, if every producer in the world were to adopt our technology, which would be great, then we would save 500 million tons of CO2 every year. So just to give you an idea of what that means, that's 2 times the emission of, let's say, a country like France. So that's really significant. And it's just by reducing by 30%, just based on the materials we already have today. So with that, here are a few references if you're interested in this work, and I'm happy to chat later. Thank you.